Related rates problems can appear in many different contexts. Like optimization problems, related rates problems are too diverse to be categorized into a finite number of problem types, although I will go over some typical problems in this lesson. Before I do so, I will outline a general procedure for solving related rates problems. The first step is to read the question and draw a diagram of the situation if necessary. The second step is to assign a letter to each quantity in the problem. It's important here to identify which quantities are variables and which ones are constants. In other words, which are changing and which are not. The third step is to find an equation relating the various quantities in the problem to each other. At this point, we should plug in the values of any of the constants. However, we should not plug in the values of any of the variables. If we plug in the value of a variable too soon, before we take the derivative, what's going to happen is we're going to get a derivative of 0, where we should have a derivative of h prime, a prime, x prime, etc. The fourth step is to take the derivative of both sides of the equation with respect to t. When I say take the derivative with respect to t, it means if you see an x, we treat it as a dependent variable, not as an independent variable. The derivative of x squared will be 2x times x prime. The fifth step is to plug in the known values for the various rates of change of the various variables. If some variables are unknown, we're going to use the original, the undifferentiated equation to find the values of them. The sixth step is to solve for the unknown rate of change, and the last step is to state your answer in words. Many related rates problems involve the rate of change of a distance between two objects. Usually this distance can be expressed in terms of two other distances using the Pythagorean theorem. In example 1, we have two train tracks which meet at a junction at right angles. We have one train which is approaching the junction, so it's called as T1, approaching the junction from the east. Its speed is 70 kph. We've got another which is leaving the junction, heading north at a speed of 60 kph. And we want to talk about how fast the distance between the trains, will be, this distance d, is changing when the first train is 30 kilometers east of the junction, second is 40 kilometers north of the junction. Well, our variables in this question is going to be the distance of t1 from the junction, which is x, and the distance of t2 from the junction, which is y. You can see the relationship between these three variables is Pythagoras' theorem. D squared equals x squared plus y squared. Now, the given information is that since the first train is traveling at 70 kilometers per hour, x prime is negative 70, because x is shrinking as the train one goes towards the junction. Y prime is 60, since the second is traveling at 60 kilometers per hour. The first train is 30 kilometers east, so x is 30, and the second one's 40 kilometers north, so y is 40. So now we're going to take the derivative of this equation. We get 2d d prime equals 2x x prime plus 2y y prime. Now we could plug all this information in, try to solve for d prime, but we don't know what d is yet. So to find what d is, we're going to plug these two into this equation. We'll get d squared equals 30 squared plus 40 squared, which turns out to be 2500. So d turns out to be 50. So now we're going to plug this all into this equation here, and we get 2 times 50 times d prime, which we don't know, is 2 times x, which is 30, times x prime, which is negative 70, plus 2 times y, which is 40, times y prime, which is 60. If we simplify this, we can get rid of all the 2's, divide both sides by 2. We get 50 d prime equals 30 times negative 40 is negative 2100, plus 40 times 60 is 2400. From these together, we got a 300 divided by 50. D prime is 6. So which that means is that the distance is increasing at 6 kilometers per hour.